Hello, my name is Jay Kinsey, and I am a judge for the first LEGO League. And today we're going to talk about the mechanical elements section of the robot design checklist. So the mechanical elements section is one of the first major sections that appears on the sheet. There's a couple of major things that are going on here that sort of dictate the general layout of the robot. So under mechanical elements, the first thing we have is architecture. Architecture refers to the general construction of the robot. There are several options here that can be circled by the judge using the sheet. One of them is skid steer, sometimes also known as tank steering, which is where you have two wheels and they either move together or move opposite or opposed to each other to do turning. Swerve crab drive is something that's more common in the FRC competitions, but it has appeared first LEGO League before. The swerve crab drive is a function where each individual wheel has effectively a caster on it that can be vectored, and so all of the wheels can be vectored at once and turned towards a single direction, and then the robot can move in any given vector. Split robot, designs tend to be less common, but can be very powerful depending on the circumstances that they're being used in. A split robot is where you have a main robot construction. Let's say you have two motors in a sort of a traditional skid steer type robot, and you use the remaining two motors available to you per the EV3 rule set to construct a second bot which is tethered to the main robot. So as the main robot is doing a mission on one part of the table, the split bot is actually off on another part of the table completing some other missions. So that way you have two robots executing effectively on the table but still using a single EV3 brick or programmable brick of your choice. A Cartesian single axis drive is also very intriguing. A Cartesian or single axis drive robot is a robot that can't turn on its own. So for example, a skid steer robot can turn whenever it wants, right, just by moving one wheel forward or one wheel backward. A single axis drive has to go into a particular mode to move in a different axis. So for example, there was a robot once that I've seen where it could put one set of wheels down to the ground and then move in the X direction, and then it could lift those and place another set of wheels down and move in the Y direction. And so by doing that, that particular team was able to minimize error from turning because the team effectively did not do any turning because they could only operate at a single axis at a time. And the final type here for architecture is the dual differential drive. The dual differential drive is not as common, maybe as it used to be, but it's still incredibly powerful if used properly. A dual differential drive, like its name would imply, has two differentials where the differential in front is coupled directly to a motor, and then there's a differential in back, which is also directly coupled to a motor. And then as the outputs on the sides come out of the differential, one side is reversed and one side is not reversed. I realize this is kind of hard to explain without a video to demonstrate, but what ends up happening is that the motor on the differential in the front, when it turns, the wheels will turn in unison, and then when the differential on the back turns, the wheels will move in opposite directions. And you can go look up more about dual differential drives and stuff on the internet. But what's really cool about this particular design is it's very easy to mix straight motion and turning motion to make a curve. So that can be very interesting depending on the different kinds of applications you have in the competition. Drivers refer to different ways that the robots move. So most common is wheels. Next we have treads. Sometimes, robots will have skids. Sometimes robots will have passive wheels. And what I mean here by passive wheels is that a robot can have secondary or extra wheels. They just don't have tread on them, for example. Right? They're fundamentally passive. Um, yeah, passive. The next type is a wheel caster. The wheel caster was used in the original NXT set, or the original NXT set for the Tribot. Um, it's basically a single wheel with some clever geometry to make that single wheel a caster. And then today we have the ball caster, which is becoming more and more common, um, and is also mechanically very simple and elegant. And then of course there's I just left another here just in case somebody does something that's not covered there. Here we have driver selection. One of the most, I would say, common questions, judging questions, is how did you select, the wheels that were chosen? Some teams will select certain kind of wheels because that's what the directions told them to do, right? So if they're building a robot from the base kit and they're using the standard robot, then those wheels that they chose would be from the directions. Some teams will do trial and error and trial and error to figure out which wheels work the best for their particular application. Sometimes you also will see teams will make graphs and charts that show, um, air over time or air over distance and things like that for particular wheels. Some teams select wheels based on intuition. They just think a certain set of wheels will be better. Some teams choose a set of wheels for precision. Some choose it for speed, or aesthetics, or load capacity. And then finally here we have wall following. So wall following is a very critical part of First Lego League. It's great for getting around the table efficiently and also managing air on the table. So most common way to do wall following are skids and rollers. Um, Simply by applying a set of wheels that live on the side of the robot and that allow the robot to run alongside the wall smoothly. That's what those are. Another very common technique is wall squaring, which is where the robot will basically run into the wall, and by running into the wall, the robot will now become square. So if it's off center a little bit or pointed in the wrong direction, the robot can then guarantee that it's at least facing a particular vector. Sensor aided is very interesting. It's not necessarily as common as the others, but it can be very useful depending on the application. It is not uncommon for teams to use ultrasonic sensors on the robot to follow the wall. And so sensor rated generally refers to ultrasonic. So the way you would use this is you would circle sensor rated, or you would just write ultrasonic or US or some other abbreviation into this area here to signify that they used a sensor rated function here for wall following. Sort of an extension of wall squaring, we have wall clamping. This wall clamping would be, instead of just having rollers that operate on the side of the wall, there's actually a whole other assembly or armature that actually goes over the wall so that the machine hugs the wall and guarantees that it will actually run against it and won't have a tendency to veer away. So this concludes the video on the mechanical elements section of the robot design checklist. Thank you for your time.